All right, so continuing looking at HL topics and probability, we want to return to the ideas of the coefficient of, well, the correlation coefficient and some ideas of regression we've talked about before, and now start to look at these topics a little bit more deeply. And there's two types of these sums of squares we talked about. There's the sum of squares of residuals and the total sum of squares. And I want to introduce these terms. And so if I look at here, I have some data here looking at comparing the number of guests at a hotel to its hotel rating. And it says you are investigating whether a hotel's rating on a certain travel website affects the number of guests the hotel has over the period of 1 year. And we have this table here. So the first thing we want to do is clearly state the explanatory variable and the responsive variable. And so these terms are new. The explanatory variable is equivalent to the independent variable. It is generally plotted on the x-axis. And the responsive variable is also known as the dependent variable, and that's plotted on the y-axis. And so we want to think here, what is going to be the explanatory variable or the independent variable, or what's going to be the dependent variable? In this case, we would imagine that the hotel rating will affect the number of guests. So in this case, the hotel rating is like our x, and the number of guests is our y. So if we were to make a graph or a scatter plot, we'd have hotel rating on our x-axis. We call it the explanatory variable or the independent variable, and guests on the y-axis. And so just to answer that, the explanatory variable, again, is the hotel rating, and the responsive variable is the number of guests. All right, so with that said, now I want to calculate this, which is the total of the sum of squares, which the way we calculate that is first we look at our responsive variable, the y, and we need to find the mean of that. So the first thing I want to do is find the mean of this. There's only 5 values here, so the mean of our number of guests, I can quickly add them up, divide by 5, and I get exactly 1,314. That's my mean. So the total sum of squares is calculated like this, where I look at each of these individual number of guests. I find the difference between this, and I square it, and I find the sum of all those. So in this case, the SS total, I find the difference, and I'll look at this first one between 1270 and 1314. Doesn't matter which order I subtract them because I'm going to square it in a moment. So 1314 minus 1270, and I square that. And I do the same thing for the next. I'll go 1314, the mean, minus 1410, and square that. And the same thing for this. 1314 minus 1380 and square, and I'll just go dot, dot, dot till the last one. So 1,314 minus 1,320, all squared. And so this is what we call the total sum of squares. And as you can see, it's just the sum of a bunch of squares. And because we're squaring everything, the order we subtract doesn't matter. And in this case, if I do all my calculations properly, I should get exactly 30,920. And we'll use that value later on. But again, that is the total sum of squares. All right, continuing with this table. Next, I want to determine this right here, which is the residual sum of squares. Now, a residual is the difference between the actual value on our y-axis and the expected. So when I find the expected, the next thing I need to do is I need to find my linear regression, my least squares linear regression. We've learned that before. And so just keep in mind again that this is my x-axis, this is my y-axis, and so make sure when you put your table in, this is your first column, this is your second column. And if we do that properly, we should get a regression equation of approximately 139 points, I'll do lots of decimals, 706x plus 866.941. And that should just take mere seconds to do on a GDC. That said, what I need to do now is use this function or use the graph and determine for each of these hotel ratings, what's the expected number of guests, and compare that to the actual. So I'm just gonna go to my table here and add a new row and just write expected. And if I have a hotel rating of 3.5, I can substitute that right here. Or I can just look at my graph of this and check the output when the value is 3.5. It's probably faster. And I get 1356. So according to our linear regression model, when the hotel rating is 3.5, we would expect 1,356 guests. And do the same thing for the rest. Put in 3.7 for x, or just find the value of the regression model when x is 3.7. And so we get 1,384 for that, 1,314 for that, exactly matching up with the mean in this case, 1,244 for that, and 1,272 for that. And so now I can find the residuals. The residuals are the difference between the expected and the actual, just the difference of these. Now residuals may be negative, they may be positive, but I want to find the sum of the square of the residuals, which means I'm going to subtract these. It doesn't really matter what order I subtract them. I'm going to square them all and then add them all up. Well, that just got messy. But in this case, I'll write it right here. So the sum of the squares for the residual will equal, again, the order doesn't matter, so I'll go top minus bottom, 1,356 minus 1,270 squared, plus the next one, 1,384 minus 1,410 squared, plus, and so on, all the way to the last one, which would be 1,272, our expected amount, minus 1,320. Keep in mind the residual is always the difference between these. If our actual value is greater than in fact, I'll find an example like that, like right here. If our actual example is greater than the expected, then our residual is positive. If the actual value is less than expected, our residual is negative. And that's what's kind of discussed right here. For example, these are negative residuals, these are positive residuals. However, if I'm just finding the sum of the squares, it doesn't matter what order we subtract them. And if I do this, I should get approximately 17,648. Actually, I think it's exact. Anyways, I'm pretty sure that's exact. Well, the last thing I want to do is now find this, 1 minus the sum of squares of the residuals divided by the sum of squares, the total sum of squares, which we call r squared, which is the coefficient of determination, which your GDC finds every time you determine a regression equation as well. And so in this case, if I want to find r squared, and I'll check with the GDC, 1 minus the value we just found, the sum of squares of the residuals, 17,648, divided by the total sum of squares, which was from the last part, 30,920. And if I calculate this, I get approximately 0.3 significant figures, 429. And then if I go back to my GDC, and you should see the same value when you found your regression model. So this matches what we see from our GDC. Now, for linear regression models, which is all I'm looking at right now, if I square root this, I will have my Pearson's coefficient. Pearson's correlation coefficient. That said, that's only true for linear. But again, when we're looking at linear regression models, this value here, if you square root it, exactly matches up with your Pearson's R. However, though, I don't ask for that anyways, so I'm done that. All right, so one last quick question. Danny, good old Danny, he's investigating whether the price of petrol, which is gasoline in the UK, affects the price of milk. He has collected this data. So we want to find, using our GDC, the coefficient of determination, that's our R squared, and then explain what it represents. Well, I'm going to use my GDC, but first I need to realize, okay, what's my X and what's my Y? What is my explanatory variable and what's my responsive variable? And so if we're trying to see if the price of petrol, the price of gasoline affects milk, then that must be my X and this must be my Y. We're trying to see if this here affects this here and to what amount. So now when I go to my GDC, this is my X column, this is my Y column. Should be really quite quick. Make a linear regression equation, and I should get R squared to be approximately 0.578. Now, you could also find the total sum of squares, find the sum of squares of the residuals, and go 1 minus that quotient, but this is way, way, way faster. That's it. What does this mean? Well, this value here, it actually tells you the percentage of how much the change in price of X affects the change in Y. It doesn't tell you if there's causation, but it does describe the correlation. So I can say this means that approximately 58% of the change in price in milk, change in price of milk, can be accounted for by the change in price in petrol or gasoline. I'll put petrol. If anyone's actually watching in the UK, I really doubt it. Then I'll put gasoline. All right, so that's what that value tells us. And in general, that's what our R squared value always tells us, what percentage of the change in our responsive variable can be accounted for by the change in our explanatory variable, or dependent and independent. Just a few new terms there. So in later lessons, I want to move beyond just linear models, but linear models are incredibly important.